in this example, we're going to do a pipe flow application with a turbulent flow. And this example is actually really a good one because it shows both conservation of energy and conservation of mass. The specific example that I have in mind is we have a water system where the length of the pipe is 600 feet. It's a 4-inch diameter pipe. It's cast iron, which if you look in the Moody diagram has a roughness of 0.00085 feet. Okay? The required flow in this pipe is 0.53 cubic feet per second. And what we're trying to figure out is what would be the required height of this water tank to deliver this flow of 0.53. This would be a very common application. It could be, for example, for a fire hydrant, or maybe this is a flow that's required for a specific application, like maybe there's a gas station or some type of business or a residential application where they require this flow and it's a single pipe that's 600 feet long. Okay, a couple other things. First of all, we know the dynamic viscosity, and we are going to ignore minor losses in this particular case because we don't really know how many 90-degree elbows we have and valves and all that stuff. We're going to really focus just on the major losses, which are friction in a 600-foot long 4-inch pipe. Okay? So I'm going to start by defining what my reference points are for the energy diagram. So I'm going to use this free surface as point 1, and point 2 will be the point just outside the pipe. Okay? And I'm going to start my solution by just writing the Bernoulli equation in its general form for those 2 points. Okay, and again, I don't have the minor loss term, I'm just going to have the friction term. Okay, couple observations. First of all, if I look at point 1 and point 2, their pressures are both going to be atmospheric. Okay, so that allows me to cancel these terms. Okay. The velocity of the water at the water surface is going to be really, really close to zero. If you just imagine you have, say, a cup of water, and you look at the water surface, it's not going to be moving a lot. And even if it was, you square that and divide by 2g, it would be really small. So for all practical purposes, V1 is equal to 0. Okay. Now, if we use this pipe here as the datum, okay, the reference point, what that means is the elevation of point 1 would be h, and the elevation of point 2 would be 0. Okay, so we'll have this out. So if I take this equation now, based on these observations, and I rewrite it, what I have is on the left-hand side, I have h is equal to, and we're going to have the V2 squared over 2g plus the head loss term. Now I'm going to go ahead and expand on that head loss term. Recall in the lesson that we learned that the most common calculation of head loss is using the Darcy-Weisbach equation, which states that it's a function of the friction factor, the length of the pipe, the diameter, and then of course the velocity head. So when I look at this equation, I can see that there's 2 things I'm going to need. I'm going to need the velocity, and I'm going to definitely need the friction factor. So we'll go ahead and start with the velocity. Okay. Conservation of mass tells us that the flow is equal, at any point the flow is equal to the velocity times the area. So if I rewrite that, I can say that the velocity at point 2 is equal to the flow going through the pipe divided by the area at point 2. Okay? So my V2 will be, the flow was given to us as 0.53 cubic feet per second. Okay? And the area of a pipe, we're going to use pi over 4, and I'm going to use the diameter. I'm going to take a shortcut here. Instead of writing 4 inches and then multiplying it by 1/12, I'm just going to write 4 over 12 feet, and I'm going to square that, right? Because the 4-inch diameter is equal to 4 over 12 feet. Okay. When I do that, I get that the velocity is equal to 6.1 feet per second. Okay. So we need that. The second piece of this equation, for me to get the friction factor, I'm going to have to figure out the Reynolds number, and then from the Reynolds number, I can use the Moody diagram, knowing the relative roughness, the Reynolds number, to look up the friction factor. Okay, so let's go ahead and say here for Calc F, the first step is to calculate that Reynolds number. Okay, we know the velocity. Actually, I'll write the equation out first. It's velocity times the diameter of the pipe over the kinematic viscosity. So we have 6.1 feet per second times 4/12 feet, right, the diameter of the pipe, divided by the viscosity, which was given to us, of 1.21 times 10 to the minus 5 feet squared per second, which is a common value for water. Okay, this gives us a Reynolds number of 1.68 times 10 to the 5th. Okay, so we have the first piece of what we need for the Moody diagram. The second piece of the Moody diagram is based on, the x-axis is based on this relative roughness. Okay, we have a roughness of 0.00085 feet. The relative term means that we divide by the diameter of the pipe itself, which is, again, is 4/12 feet. And that gives us a relative roughness term of 0.0026. Okay, it's unitless, okay? So essentially it's like a percentage. So now if we look at the Moody diagram, and I don't have a Moody diagram on me right now, but we've done several of these in class. If you look at the Moody diagram and the y-axis with the relative roughness and the x-axis with the Reynolds number, okay? So from the Moody diagram, okay, we figured out that the rough frictionless factor comes in at about 0.026. Okay. So now we have everything we need. We know what the friction factor is. We know the velocity term. We can just go back to the original equation, substitute the terms in, and get our answer. So we have a value of 6.1. Again, I'm going to write the units throughout. Feet per second squared divided by 2. Gravity in English units is 32.2 feet per second squared, plus, and then we have the friction factor, 0.26. The length of the pipe is 600 feet. Okay, the diameter of the pipe is going to be 4/12 feet again. There we go. And then we have the velocity head, which is the 6.1 squared over 2 times the 32.2. Okay? And when we plug this into our calculator, we come up with a final answer of 27.6 feet. Okay, so what we're saying is in order for us to deliver a flow of 0.53 through 600 feet of 4-inch cast iron pipe, we would have to have a water elevation, or the elevation of the water tank would have to be at 27.6 feet. And that concludes this example of a turbulent pipe flow application.